For today's video, we'll be talking about hydroboration-oxidation for alkyne. And so for alkynes, when drawing the mechanism for this, we will get something called base catalyzed hydration or base catalyzed tautomerism, right? So before we start, we should know that this is called a terminal alkyne, right? Because terminal means end, and so this is a triple bond is at the end of a carbon, right? Then we have something like this, and this is in the triple bond is between two carbons, right? So there's 1, 2, 3, 4 carbons over here, and it's 1, 2, 3 carbons over here, right? But the point is that the triple bond is between 2 and 3, right? It is not at the end, or it's not at the beginning, or this can be at the end as well. It is in the middle. This is called internal. And so from here we have actually, if it's terminal. For a base catalyzed hydration, it will be an aldehyde will form, right? An aldehyde. But if it is internal alkyne, it will form a ketone, okay? A ketone. And so we'll get more into this when drawing its mechanism. But for example, if we start out with a reaction, a simple reaction as this, and so this is a terminal alkyne, and so for this, it would be reacting with reagents 9 BB9, okay, and also we would have the peroxide coming in, so H2O2 with NaOH. Again, this is there is actually different reagents used. Different textbooks use different reagents, and so for this, we're going to use this reagent for this video. So refer back when we were doing this for acid catalyzed hydration, we made a ketone, okay, but we use different reagents. We're going to use the same molecule, but we're going to use the hydroboration-oxidation reagent for this. So this will still make an enol, right? But this time we have the peroxide, which this makes it anti-Markovnikov, right? So it's anti-Markovnikov, and so now the OH would go on the carbon that has the least amount of substituents. So if we look back here, this carbon over here is a secondary carbon, which is connected to 1 and 2 carbons, while this carbon over here is a primary carbon that's connected to only 1 carbon over here. So in fact, the OH will now go on the least carbon that has the least amount of substituents over here, okay? And so this is still an enol, right? So we still got a carbon with a double bond and connected with an alcohol. So we have an enol form, okay? We will always form an enol first. Then this will go into something called Tautomerism, which is rearrangement of hydrogen in double bond. So from here, we have a terminal alkyne with the start. So this will form an aldehyde. So this will have a of this, and now the H hydrogen will go over here, and this is called an aldehyde. Okay, we form an aldehyde, and so this is our final product for this structure. Now let's redraw the structure, but differently. Now the triple bond is in the middle, right? Okay, so this time it's still reacting with the same reagents. Okay, 9 BBN and H2O2 NaOH. Okay, so redraw the thing and make an enol. This time we're going to have 4 carbons, okay, because there's 1, 2, 3, and 4. This had 1, 2, 3, right? So our group would actually count as a carbon. I forgot to write over here. Give me a second. Okay, and the R group's over here, right? So the double one would be between here. So now we can either put the carbon, because this carbon over here is secondary, so this carbon over here is also secondary. So we can either put the carbon over here or over here. But I'm going to pick one for now for an example, right? So this, we made an enol form over here. Now, we can't make this into an aldehyde because you can't have an aldehyde in the middle. So in fact, we're actually going to make this into a ketone going into tautomerism. So this is our final product for here, and this is a ketone. Okay. So again, when we have internal alkyne, it becomes a ketone, but when we have terminal alkyne, it becomes an aldehyde. Okay. I'll show another example here. If we have this structure, right, we have a terminal alkyne, and it's still reacting with the same reagents that we had been using, 9BBN all over peroxide and NaOH. Okay, so from here we would draw the structure, original structure, and we would draw this in an enol version. Double one will go here. Oops. So we would have the OH on the carbon that has the least amount of substituent. So we have the enol formed, and from here we would make it into an aldehyde. Okay, because it's a terminal alkyne. Okay. And the hydrogen is coming off the same carbon. So this is our final answer, a major product for this problem. Okay, let's try another example. Okay, we still have a terminal alkyne here. Still using the same reagents, 9BBN over H2O2 NaOH. So for this, we would get this structure. We'll have a double bond over here, and the OH over here. Okay. And so from here, we make this into a aldehyde because we have terminal. O, and then the H coming off right here. So it's our final answer as an aldehyde. Okay. Let's do another example, but this time something else. If we have this structure over here, right, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. We see that if we cut it in half, we have symmetry. The left side and the right side look alike. But we also know that this is an internal alkyne, right? This because it's in the middle. It's not terminal, but it is in the middle. So from here, it would give a reaction. If we reacted with the same reagents, right? 9BBN all over H2O2 NaOH. So redraw the molecule in the carbons between 4 and 5 carbon. From here, actually, no, yes, we'll put that here. From here, we actually know that both of these carbons are secondary carbon, so it doesn't matter where we put it, the OH, so I'm going to put it here. And so from here, we know it's in the middle, so we can't make it into an aldehyde, and therefore we will change this into a ketone instead. And the hydrogen will come off over here. Okay, so now we have made a ketone instead of aldehyde. Right? Again, the reason for this is because our alkyne was an internal alkyne, right? This was an internal alkyne, and therefore we made a ketone instead of aldehyde. So let's do one more example. if we have this structure, oops, go up. Okay, now we have this structure, right? Let's count the carbons we have. I'm just gonna start here. 1, 2, and 3, and 4 carbons, right? So this is not terminal. This is an internal alkyne. So from here, if it's reacting with the same reagents, redraw the structure, right? And this time, if we cut it in half, we don't have no symmetry, right? The left side does not look like the right side. So from this, we would have it is not symmetrical, but also we know that it is actually both of the carbons have it's a secondary carbon, so they have the same amount of substituents. The double bond would be here. So this carbon over here is a secondary carbon, while this carbon over here is a secondary carbon because it's connected to this and that. The other one is connected to this and that carbon. So they both have the same amount of substituents. So that means you can either have the OH over here, but also it has this enantiomer, which is this coming off over here. So from this, we'd both get in a reaction of not forming an aldehyde, but actually form a ketone again because it is internal alkyne with the start. And so we would have an enantiomer, which would be and a hydrogen. You don't have to draw the hydrogen, but always assume that it's there. And so this is our final product. We have 2 final products for this answer, for this problem. So in drawing its mechanism, let's start with the basic structure. Okay, you have an R group and you have a terminal alkyne, right? And this is reacting with the same reagents we have been using. 9BBN all over H2O2 and NaOH. Okay, so many other textbooks use different reagents. This is the one we'll be using for today. So again, our first step is to make this into an enol. Always make it into an enol, but this is an anti-Mark carbon so it goes on the carbon that has the least amount of substituents. So like this. And we have the enol formed, right? This is what we want to start with when drawing our mechanism. So from here, the first thing we would do is use a reagent that is base. So for this case, we would use OH. It's a very good base to use. Negative charge. The first things first, the lone pairs on the oxygen will go on that hydrogen, which will give off the electrons to oxygen in this case. This will form a reactant of oxygen having 3 lone pairs and a negative charge, double one still here. From here, we would use water because we made water from this. And so from here, the electrons from oxygen would go and form a double bond over here. This double bond will grab that hydrogen, and that hydrogen electron will go give off it to oxygen. So from here, we will get a reaction of a double bond forming here with 2 lone pairs on oxygen and the hydrogen that we have grabbed. Okay, but also we'd add this with our OH that has been formed because we had made it from here. Okay. Also, there is the hydrogen over here. Actually, the hydrogen over here because it was grabbed from here. That's why we drew it here. Actually, this hydrogen over here, it wasn't grabbed, but it was always a hydrogen over here. Always got to assume there's a hydrogen here. Okay, and this will make it an aldehyde. Okay, so this is our answer, and so we made an aldehyde. Aldehyde. Let's try another problem, and for this we would use the original structure here. Okay, we'll use this. Okay, so for this, it's still reacting with our reagent that we had been using. So 9BBN, and this is all over H2O2 and NaOH. Right, from this, we redraw the structure, but have it into an enol. OH would be on the least carbon that has the least amount of substituent, and there's the enol that has been formed. So from this, we would start this with the mechanism. OH, the first things first, the OH would come, hydroxide, it would come and grab that hydrogen. Oops, let me draw the hydrogen better. It would come and grab that hydrogen. That hydrogen electron will give off to that oxygen, which will give us a reaction of forming a double bond here. Actually, no, not yet. So for this, we actually have to, it would be an oxygen. We're having 3 lone pairs, and with a negative charge, and also we still have that double bond over here. Now from this part, all we have to do is bring in the water that we had made. Water. And now from this part, one of the lone pairs from oxygen goes and makes a double bond here, and the double bond that we already have grabs that hydrogen, and one of the electrons of the hydrogen goes to the oxygen, forming a OH minus. So our final product would be, okay, this hydrogen is always here, but I'm going to show it to indicate the aldehyde, and the hydrogen that was grabbed from here is now on the carbon that has the most amount of substituents, that is here, like this. And also we had made OH hydroxide ion that we had made from the product. So our final answer would be this, an aldehyde plus an OH group. Let's try as one more example. And for this example, we're still reacting with the same reagents, 9BBN over H2O2 NaOH. We have an internal alkyne over here, so this means it will not become a aldehyde, but this will become a ketone. So this is a base catalyze tautomerism. This is why we redraw the structure for this. Let's make it into an enol first. Oops. Okay, so we have this, and then it's between here. And so for this, before we do anything actually, we should see that over here, we don't have symmetry because this side is not the same as this side. And so for this case, this is not symmetrical, okay? That's one thing. But also, this carbon, both of these carbons are actually secondary, right? They're both connected to this. This carbon connected to this, and that carbon. This carbon over here is connected to this and that carbon. So they're both secondary carbons. So this means that they have the same amount of substituents. So therefore, we have an enantiomer, right? So this plus this enantiomer. For this, I'm only going to draw one of its mechanisms, and then redraw its other enantiomer at the end. So I'm going to pick here. And so from here, it's a base catalyze tautomerism. So this is why we add the OH group. And it has a minus charge. So first things first. Actually, let me change that. OH. Okay, and then we would have an O and then an H over here. Has two lone pairs. One of the lone pairs of oxygen will go grab that hydrogen. This hydrogen gives us electrons to oxygen. So from this, we would have a structure that would look like this. Still has a double bond. Now this oxygen has 3 lone pairs with a negative charge. And this is where the water comes in that we had made. Water comes in right over here. Now the oxygen, one of its lone pairs of oxygen over here, the negative charge goes and it makes a double bond over here. Well, this double bond goes and grabs one of this hydrogen and gives off its electrons to that oxygen, will give us a final product of this, forming a ketone this time. Okay, ketone. As you can see, we didn't use an acid catalyzed hydration. We use a base catalyzed. Hydrogen over here. Okay, we have this, and also actually plus the OH that has been made, the hydroxide ion, right? So this is our answer, but also plus is an enantiomer, which is and a little double bond over here, and also plus OH. Okay, so this is a base catalyzed hydration. And so from this, we started with its enol, right? It's enol. Done the mechanism, and we have done its products, shown as products. And so from this, we have our final answer. Again, when we have terminal alkynes, we would form an aldehyde. If we're internal alkynes, we would form a ketone. And this is only for base catalyzed tautomerism.